Welcome to today's Explainer. We're diving into a fantastic resource called the Number Lantern. You know, if you're a parent or caregiver, third grade math can kind of feel like a massive hurdle, right? Suddenly, the kitchen table turns into a battleground of tears. But it absolutely doesn't have to induce math anxiety. Today, we're going to look at how to support your child's learning by shifting the whole focus away from speed and rote memorization and toward true visible understanding. And this brilliant quote right from the intro of our source really sets the stage perfectly. Math is not a stack of tricks that children must memorize before they are allowed to understand. Let that sink in for a second. Math is not a stack of tricks. Instead of just drilling flashcards endlessly, math is really about noticing what stays the same, what changes, and how quantities actually fit together out in the real world. Think about a grocery receipt, a game score, or even a bus schedule. Those are all everyday windows into mathematical thinking. So, to build that kind of thinking, we kind of have to rethink some of the basics. Let's start with estimation. We so often treat estimating as just a wild guess or maybe a chore you do before getting the real answer. But we really need to redefine estimation as a crucial mathematical guardrail. Think about it. A guardrail doesn't steer the car, but it keeps you from flying off the cliff. If a classroom has 186 craft sticks and gets 74 more, estimating 200 plus 70 tells us the answer should be somewhere near 270. So if the exact calculation spits out 2600, that guardrail immediately tells you, whoa, something went wrong here. Maybe a misplaced digit or a forgotten regrouping. To really build that mathematician's mindset at home, try using this simple four-part check. After solving a problem, kids should ask themselves these four things. 1. The situation. Did I even answer the right question? 2. Size. Is my answer anywhere near my guardrail estimate? 3. Calculation. Can I verify this with a second method? And 4. Unit. Did I actually name what this number measures? That last one is huge, by the way. The number 4 by itself doesn't really mean anything. Is it 4 meters, 4 apples, 4 backpacks? Writing the unit is what actually finishes the thought.
Section 1. Decoding base 10 operations.
All right, to see how all this builds, let's decode how addition, subtraction, multiplication, and division are all fundamentally connected by equal groups and our base 10 place value system. Let's look at subtraction. Subtraction is not just the rule of larger digit minus smaller digit. That mindset leads to major errors. Kids will see 52 minus 38 and just subtract 2 from 8 because, well, it's easier. We have to show that subtraction actually has 3 totally distinct meanings in the real world. It can be takeaway, like having 640 stickers and using 185. It can be compare, like one class reading 640 pages while another reads 185. Or it can be a missing part, like having a goal of reading 640 pages and having already read 185 of them. Same exact calculation, but completely different physical meanings. Now, this brilliantly illustrates division as sharing. We can clearly see 24 objects shared equally right into 6 groups, which leaves 4 in each group. Our source points out something super important here. A diagram like this isn't just cute decoration for a worksheet. It literally holds the mathematical relationships while the brain does the heavy lifting. If you know the total and the number of groups, you are dividing to find the amount in each group. Actually drawing it out prevents division from just becoming a disconnected list of facts to memorize. And what about when we multiply larger numbers, like 36 by 24? An area model visually breaks down numbers into really digestible parts, which we call partial products. You can literally see a rectangle split up. 36 becomes 30 and 6, 24 becomes 20 and 4. You multiply those parts to get 600, 120, 120, and 24, and then you just add them all up to 864. The beauty here is that this isn't some separate, weird trick. It perfectly matches the exact logic happening invisibly inside the standard written algorithm. It makes the invisible totally visible.
Section 2. Beyond whole numbers.
Once we have a solid grip on whole numbers, we can stretch those exact same ideas even further. A massive takeaway here is that fractions and decimals are simply numbers on a line. They're not just shaded pictures of pizzas. By placing a decimal number line right next to a fraction number line, we instantly see their shared DNA. On one side, the distance from 0 to 1 is cut into 10 equal intervals, tenths. On the other, it's cut into 8 equal intervals, eighths. Both notations represent exact locations and exact distances between 0 and 1. When a child learns to see 3/8 as a specific distance on a line, rather than just 3 shaded slices out of an 8-slice pizza, they actually stop doing things like adding denominators together by mistake, because the size of the pieces doesn't change when you add them, only the count does. Section 3. Measuring the physical world. We use all these concepts to measure the physical world around us, and measuring comes with its own fascinating set of rules. Take time, for instance. Time is incredibly tricky for kids. Why? Because our clocks do not run on a base 10 system. 60 seconds make a minute, 60 minutes make an hour. So if you try to subtract 9:45 from 10:15 using standard base 10 stacking, you might end up with 70 minutes, which obviously makes absolutely no sense. That is why a timeline is essential for calculating elapsed time. You start at 9:45, track the jump to a friendly number like 10 o'clock, which is 25 minutes, and then add the remaining 20 minutes to get to 10:20. Total elapsed time is 45 minutes. Doing it this way prevents that base 10-hour mistake entirely.
When it comes to mass, appearance can be incredibly misleading. A giant empty box might be way lighter than a tiny rock. So we rely on tools like scales. But here is the absolutely crucial point for reading any scale, bar graph, or ruler. We have to teach kids to determine the value of one small interval before ever reading the pointer. Look at a standard scale where the marks go from 0 to 250 with 5 spaces between them. That means one single interval represents 50 grams. So if a pointer is 3 ticks past 500, it isn't 503, it's 650 grams.
We see this exact same need for precise measurement in geometry too. We classify shapes, like isosceles and equilateral triangles, by measuring their exact properties, not just by glancing at them to see how they look. Mathematics relies on properties, not just appearance. An isosceles triangle has at least 2 sides of equal length, while an equilateral triangle has all 3 sides equal. By actually getting out a ruler or a compass to prove these lengths, kids learn to argue with hard evidence rather than just saying, well, it looks pointy. And speaking of evidence, reading data properly is such a vital life skill. Look at a transportation bar graph. Just like the scale we talked about earlier, we check the scale of the graph first. Say, one interval equals 5 students. We really need to remind kids to state the facts from the graph first, like the green bar represents 25 students who walk, before they jump to wild interpretations like, oh, green must be everyone's favorite color. Data tells us specific, measurable facts, and we need to separate those facts from our own assumptions. Now, to connect all of these concepts visually, our source introduces the Japanese soroban, or abacus. This offers such a powerful, tactile view of how quantities trade across our base 10 system. Take the number 3,407. You'd have 3,000s, 400s, an empty tens rod holding the 0 place, and 7 ones. The physical, hands-on act of sliding these beads to make 10 and then trading them for one bead in the next column, it makes the completely abstract idea of regrouping totally concrete for kids.
Section 4. The Family Math Lab.
So, how do we actually bring all of this home without turning your kitchen table into a high-stress testing room? A lot of it just comes down to how we ask questions. Instead of jumping straight to demanding speed or just asking, what's the answer, try changing your prompt. Ask, what did you notice first? Or, can you show me the same idea another way? And then, and honestly, this is the hardest part for us adults, just wait. Give them several seconds of total silence. A pause gives a child the breathing room to actually build an idea rather than just panicking and guessing what they think you want to hear. So here are your core strategies for home support. Wait for answers. Focus on drawing the diagram. Always estimate the size of the answer before calculating. And most importantly, celebrate corrected mistakes. As the source beautifully states, a corrected mistake is evidence of learning, not evidence that learning failed. If you focus on the process, use those visual tools, and strip away the timed pressure, everything changes. Mathematical growth is about strategy use, not just about being a fast calculator. So I'm going to leave you with this to ponder. As you go forward, what single question or visual strategy are you going to introduce tonight? How will you change the way you talk about math at the dinner table so your child starts seeing it as a beautiful, logical language rather than just a chore? The next time they get stuck, will you rush in to give the answer, or will you give them the silence they need to find it themselves? Thank you so much for joining me on this explainer, and happy learning.